Hello, good morning everyone. Today still the weather is cold, but it is a beautiful day and the sun is shining. Today we will continue on Taylor's expansion on Taylor polynomial. We are in this week, so a part of this week we will go through Taylor, then we will try to finish the part of the inverse function tomorrow, inshallah. Time is ticking within, we have the next week, and then we will have our first midterm, which represents 25% of the total mark. The good news is we will have a break after this midterm, inshallah. So please try to study as much as possible and be ready for your coming exam. I would recommend seriously to use your hand in writing the polynomials, although these topics are really very easy, but it needs you to focus as much as possible and also to use your hand as much as possible. So try to resolve these problems and to go through some problems in the workbook by your own. This is really very important. Also, you have everything on model, so in regard for the lectures and for the assessments, previous exams, the workbook, there is some videos that's recorded on model if you want to review a part or a slide or something like this, plus all the recorded lectures, you will find them on the YouTube, so you should be in a very good shape. I will start with you to remember about what's the Taylor polynomial all about. It's really very simple, but I need you to understand the difference between these two polynomials or these two expansions in writing, and also I want you to rewrite them more than once. So if you look to the first polynomial of the first expansion, it's gonna be in terms of the derivatives and the brackets of x minus a. Once more, this is an expansion, a polynomial expansion of f of x in the neighborhood of a point which is a. So f of x as a polynomial of order k should be f of a, then plus f dash a times x minus a plus 1 over factorial to f double dash, which is the second derivative of the main function at the point a. This is the value, and it's going to be multiplied by x minus a to the power of 2. And a similar manner for the third, fourth, up to the kth term. This short handwriting for this polynomial can be rewritten also in another form, using the differential operator, which is d. If you remark, you will find that both f dash of a and x minus a are included in this form. So I would deeply recommend that you write them 2 times. So I can do exactly, I want you to do exactly like me. So I can say that for b of order k around the point a, it's gonna be f at a plus, if I won't write the derivatives directly, I will write f dash of a times x minus a. As you can see, it's like a train, so it's gonna be f double dash of a times x minus a to the power of 2. Don't forget, divided by factorial 2. And so on till you reach fn at a times x minus a to the power of n, divided by factorial n plus the remainder term. If you didn't add the remainder term, this should be approximately. But we add the remainder term to be sure that this expansion equal the main function. So I can say that at this, which is bk plus the remainder term, it's gonna equal to f of x. In a similar manner, if I want to rewrite, but with the derivative index, I can do it. We can say that f of x, the function f of x, equal the polynomial of k at a plus the remainder term, and I will write the first term exactly the same, but for the second term, it's enough for me to write d number 1 at a. which is at x, at x minus a, which means that it is the derivative and the times the part of the polynomial. So exactly the same way as you can see. So it's a d of x minus a, of course, for the function which is f of a. Plus, I can write for the second term d square of x minus a for an f of a, and so on till we reach d of, if we are talking about k, so once more, so it's a dk for the term x minus a for an f of a plus the remainder term as I told you. This is exactly what we did in the previous session. We did all of this. So let us denote Rn, the approximating error or the difference between the polynomial and the main function as I told you. So f of x should be equal to either anyway or anyhow you write your polynomial. So this is Taylor polynomial plus the remainder which is Rk. So if I want to write Rk or Rn for R of k, which is R of order k, as a function n x minus a, it would be like this: 1 over k plus 1 factorial times f of k plus 1 at point C, and this is times x minus a to the power of k plus 1. So actually it is the term k plus 1, but at point C, where point C is, or at value C, where C is less than x and greater than a, or C is greater than x and less than a. Either these two cases will be sufficient. So this is for the remainder term. So for the Taylor remainder term, it's going to be, as I told you, Rk of f x minus a, 1 over k plus 1 factorial, as you can see, times the derivative. Once if you are taking the kth term polynomial, so it's going to be the derivative which is greater than k by 1. So it's an fk plus 1 at c times x minus e to the power of k plus 1, where c is greater than a but less than x, or vice versa, c greater than x but less than a, and that's the remainder term. Okay, now I have the remainder term in between these values. Okay, if I want also to write it, this is the main equation, and that's the term which is the error or the remainder value of this term. Remark, if we are taking k equal to 0 for a polynomial of approximating polynomial of k equal to 0, this is going to be, or this expansion will change to the mean value theory. So if I want to have k at k equals 0, which means it's just only the first term. So f of x at this point will equal to f at a, then plus the remainder term. The remainder term at this time, it's going to be the term next to f of a, which is going to be simply f dash at c times x minus a, which stands for the mean value theory that we talked in the previous lecture. This is one of the nicest remarks about this issue. Okay, so if I want to see how the polynomial approaches the values or become near, really very near to the values of the function, so it's a very good approximation to the main function, it can be seen that if f such that a domain belongs to R from R is a ck plus 1 function at A, the approximation error in this case will be simply the difference between the main function and its expansion. This is the error term. And the error term is infinitesimal of higher degree, which means it grows very, very small, or it tends to be 0, maybe, I'm sorry, not maybe, but more than or faster than x tends to it. And this can be easily proved proved from the limit of x tends to a for the error term, which is simply, it's going to be f of x minus the polynomial of the Taylor polynomial of order k at a, which is divided by x minus a to the power of k. If you take the limit of this function, you will find it equal to 0. And also remark that the difference between the main function and the polynomial is that remainder term. So it's exactly either this form or limit x tends to a for r of k, and x minus a divided by x minus a to the power of k. Either any of those, it's going to be the result. The result will equal to 0. So that means that Taylor polynomial of degree k converges to 0 faster than the distance to a powered to k. And that's a proof for this. We will see more applications and we will see problems on this remark just in a few seconds once we go to the general case of approximating the functions from Rn to R. In the previous lectures, or in the previous part, we talk about the expansion using the Taylor expansion from R to R, from functions running from R to R. Like, for example, f of x equal e power x, f of x equal sine x, f of x equal x squared plus x plus 4. And one of the nicest remarks that if you try to approximate a polynomial, you will end up having a polynomial from the same degree if you try to expand to the power of this polynomial. And we will see this also in the workbook. Now, let's go to the functions that are going to be run, and we can get the approximation for it if it runs from Rn into R. So, if I'm moving or maybe mapping some functions from Rn into R, we can use also Taylor's polynomial to approximate these functions. So the approximation in this case will be, or the approximating polynomial will be as this form. So if I want to approximate f of x, which is from whatever the dimension into R, simply it's going to be either b1 of a, if we want to approximate using a first degree polynomial, f of a, which is the value of the function at point a, whatever point a, if it was 2 dimension, so it will contain x and y. If it was 3 dimension, you will find point a represented by x, y, and z, and so on. So this is the general point that I'm substituting at. Then I will use my knowledge into composite functions and do partial derivatives to get the first derivative of this function in the neighborhood of the point that we are talking about. So it's going to be d of x minus a f of a. And it's exactly the same, like f of a plus the gradient of f of a, which similar to f dash of a times x minus a. And it is written also beside it. So anyhow, it's going to be the Taylor polynomial in this case. In this case, at z, which is the b1 of x at point a, is the equation of the tangent plane to the graph at the point a and f of a. Same way like what we did in R to R, it's exactly the same once you are moving stuff from Rn into R. So if you want to find Maclaurin polynomial, for example, all I have to do just to make the substitutions round or in the neighborhood of the origin, as we did previously with Maclaurin expansion in from R to R. Let's see more if we want to have a second degree or a third degree. And I want you to remember how we do the derivatives in this case. This is why we have more than one problem. Of course, also, if we get the first order polynomial, it's going to be the tangent plane at 0 and f of 0 at this point. If you want to get Taylor expansion, but of second degree, all I have to do is to write it this way. It's going to be a b of 2 at a for the function, which is in x or whatever, or in general xyz, xy, and it's gonna be f of a plus a d. Remember the d, which contains the derivatives times the bracket, which is gonna be d at x minus a, and then for the function f at a, and then plus I will get d of 2 at x minus a, and once more times f of a, or the value of function. But don't forget that all this will be divided by factorial 2, and for the third term it's gonna be exactly the same way like this is d of x minus a f of a, 1 over factorial 2 d2 x minus a f of a. But for the third we will have exactly the same. So before we see it, it's going to be plus 1 over factorial 3 d3 of x minus a times f of a, in a similar manner as I told you. And if you want to extend your exponential till k, it will be exactly the same. Same also goes for the remainder term. So if I want to get the remainder term, it's going to be exactly the same. It's going to be rka at x minus a, and it's going to be the term which is k plus 1. So if you are seeking a polynomial of degree k, the rk of a at x minus a, it's going to be the limit of x tends to a, whatever the dimension, of the function f of x minus the polynomial in k, which stands for r, and the r is going to be 1 over k plus 1 factorial times d of k plus 1 from x minus a for an f of c. But c at this time, I can use the c value in the case of composite functions, which is c equal to theta a plus 1 minus theta times x, where theta runs greater than 0 and less than 1. And this is the limits that I'm telling you about, which means that your remainder term tends to be 0 as much as you increase the terms in your polynomial, in your expansion. I believe we are in need to see, and also same way like what happens in R to R, it's also for k equal to 0, we will end up having the mean value theory, but it is in general form. I think for the time being, we really need to have a problem or an example to see what's going on if we are moving from Rn into R. I will start with this example. This is really very important, and I want you to go through it step by step. But before going through it, I want you to know that if I have in 2D or 3D, let's keep it for R2 into R. If I want to have D2 of x minus a, this term, how to be expanded? In case of I have the main function that I'm trying to expand, it is from R2 into R. So if f such that from R2 into R, for example. So if I want to get this term, or let's start first with the D1, it's gonna be partial f partial x plus partial f partial y, but don't forget this is gonna be times x minus a, and this is gonna be y. Let's say x minus x1, and this is gonna be y minus y1, where x1 and y1 are the components of a. So if a is x1 and y1, this is what we mean by the d of x minus a. Because at this time, you will need to find the partial derivatives, or the first derivative will be a composition of these partial derivatives with respect to its components. And if I want to have the second term, this is really very important, for the second term of x minus a, I will need to expand this in front of you, which is going to be simply the second partial derivative of f with respect to x squared times x minus x1 to the power of 2 plus a 2 times partial the second derivative of f partial x, partial y, or vice versa, times x minus x1, y minus y1, then plus partial 2 of an f, partial y squared, which is times y minus y1 to the power of 2, and this is for the second degree of the polynomial. This is the second part. So once more, if I get back into these slides, okay, just less than a second, I want to get this one. So if I want to do a second degree, this is the terms that I'm telling you about. That's the expansion of this term. So it's gonna be simply the second will be the second derivative of f with respect to x squared times x minus x1. Once more, don't forget that I'm expanding or getting the expansion near or in the neighborhood of point A, and the point A here, as we are moving from R2 into R, it will contain x1 and y1. This is why we made this substitution. The question is, if I went to the third term, okay, and the third term, it's going to be d3 by x minus a. How to get this term in this case? For this term, I will need to have the third term expansion for these two functions. And in such a case, d3 of x minus a, it's gonna equal to, it's a relation for the binomial. So if you remember the binomial expansion, let's say for x minus y, for example, to the power of 2, the binomial expansion states that we have 2 and 0 combination times x to the power of 2, then plus, I will say 2 combination of 2 and 1, x times y, then plus, it's gonna be 2 and 2, x to the power of 0 and y to the power of 2. As you can see, each term, the power of x will decay and the power of y will increase, starting from y to the power of 0, y to the power of 1, y to the power of 2. In a similar manner, if I have x minus y to the power of 3, and I want to find the binomial expansion, it's gonna be 3 and 0 of x cubed, then plus 3 and 1, okay, of an x squared times y, then plus 3 and 2 of an x, just only x times y squared, then plus 3 and 3, x will be to the power of 0 times y cubed, which stand for the following. This means it's gonna be 3, it's a combination 3 and 0, so it's gonna be 1, so this term is gonna be x cubed. For that term, we will have just only 3, x squared and y. For that term, it's gonna be 3xy squared, and for the last term, it's gonna be y cubed. I want you to remember that if I'm doing a combination, because sometimes we forget this, for k and n, for example, it is factorial k divided by factorial n times the difference between them. This is the value of the combination which brings you these values. If you want to do the binomial on a second term, it's going to be like expanding a perfect square. The first square, the last square, times the first, second, times 2. So if I want to do this in here, it's going to be exactly like the following. Let's keep this plus and that plus to keep the signs in okay, because if you have minus, it will change the sign. But just in case, this one is going to be a 2 of an x squared plus, 1 of x squared. This is going to be a 2 of an xy, and that one going to be a y squared. This is why here in the expansion or in the derivative, you find we got the second derivative of f times x minus x1 to the power of 2. Then I multiply 2 with the factor, which is the factor of partial 2f, partial x, partial y, times the 2 brackets, and then the last term. Same way like will happen now. So if I'm trying to get the third term, it's gonna be partial 3 of an f partial x cubed, And then it's gonna be times x minus x1 to the power of 3. Then I will go for the second term, which is gonna be a 3 as a factor, which is first. Then I will have partial 3 of f, then partial x squared, partial y. So it's matching what's going on here. And it's gonna be times x minus x1 to the power of 2. See how the powers are related, times y minus y1, and then I will go for the second term, or for the third term, I'm sorry, which is gonna be exactly like 3, it's gonna be 3, partial 3 of an f, partial y squared, then partial x, and in a similar manner, I will have x minus, let me rewrite this, because I want to keep the same letters with you to make it easier for you. So it's going to be partial 3f, partial of x, partial y squared, so it's going to be x minus x1 times y minus y1 to the power of 2, and then finally I will have partial 3 of an f, partial y cubed times y minus 1 to the power of 3, and that's for the third term, and so on. So, if you want to have more terms, you will have to grow like this. So, this is really very important, and that's the only trick that you can find in this part. This is the only trick that you will find. So, starting from B2, then going to BK of A at X, same expansion, same everything, same steps as you can see. Okay, perfect. Once more, let's get back to our problem. So here, he's telling you that I have f from R2 into R, and it is defined by the function f of x over y, which is 1 divided by 1 plus x squared plus y squared, and define the Maclaurin polynomial of degree 2. I will also add to show you, or I will add extra step to make you see how the terminal or the remainder term is going to decay, tends to 0 or whatever, as you will see. So let's start by making this function step by step. I would like to leave this as it is, but I'm using this part much, so I will erase it and I will rewrite it with you step by step. So once more, let's start from scratch, doing everything step by step as I told you. Okay, so once more, I have f here, which represent r squared into r, and the function for the time being, which contains two values, f of x over y, is equal to 1 divided by 1 plus x squared plus y squared. So I want to start, we need to find Maclaurin polynomial of degree 2, which means I will have to get till the second derivative for a polynomial, for Taylor polynomial. So I will start like this. First of all, I will have to get f sub x. So I'm going to get f sub x. In this case, I have 1 divided by 1 plus x squared plus y squared. I can rewrite it to be in this form, 1 plus x squared plus y squared to the power of negative 1. So if I want to make the partial derivative with respect to x, all I have to do is to differentiate the main function, so it's going to be a negative of a 1 plus x squared plus y squared to the power of negative 2, then times the derivative of what's inside this bracket with respect to x, so it's going to be a 2 over x. But this is just f sub x. I will have to do the same to get f sub y, which stands for the first derivative. So I will try to go, I can rewrite this, of course. So it's going to be a 2 over x divided minus 2x divided by 1 plus x squared plus y squared for an f of x. Similar manner for an f of y. So it's going to be same way like I will start to differentiate with respect to y. So it's going to be 1 plus x squared plus y squared to the power of negative 2 times 2 over y. So if you write this, it's going to be negative 2y divided by 1 plus x squared plus y squared. If I want to prepare for getting the Maclaurin expansion, so I need to find f sub x, f sub y, but at the point 0 and 0 as I'm doing Maclaurin expansion. So, which leads to, that's f sub x at 0 and 0 will equal to 0, of course. Why 0? Because you will start substituting instead of x and instead of y by zeros. So it's going to be a 0, and this is 0 and 0. So it's going to be 0 divided by 1. So the result will be just only 0. Doing exactly the same with f sub y. So what I have to do now is to start getting f of y at 0 and 0. And the result also will equal to 0 in a similar manner. So now I'm ready. I have f of x at the point 0 and 0, f sub y at 0 and 0. This is for the first, or for a polynomial of first degree. But I need to find a polynomial of second degree, which means that I will need the second derivative. So for the time being, I will leave those as it is, and I will start now to prepare for the second term. The second term will contain, for the second degree, I will need the second derivative, partial derivative for all this function. Which means that I will need to have f xx, and I will need to have f of x and y. Then I will have to get f yy, or partial to f partial y squared with it. So I will start with this one. Start differentiating this guy. Of course, this is to the power of 2. I forgot to write it, so please be careful about the power, because this is negative 2, so this should be power 2, and this should be power 2. I will start differentiating at the time being. So all I have to do is to use the derivative law. So I will square the denominator, which is going to be to the power of 4, 1 plus x squared plus y squared. Then I will start differentiating the denominator with respect to x. So differentiating with respect to x is going to leave you with negative 2 times the denominator, which is going to be 1 plus x squared plus y squared. Then a minus sign. For the denominator will remain the same, negative of 2x. Then I will differentiate the denominator, which is going to be 2, and 2, which is going to be a 2. I will have times 2 times 1 plus x squared y squared. Then times 2x, so I will have 4 of x right here. And then I will try to simplify things a little bit. So once more, this is the derivative of the denominator. It's going to be a negative 2 times the denominator, which is 1 plus x squared y squared to the power of 2, exactly the same. And I did for the second part, leaving the denominator negative 2 of x. Careful, very careful with the signs and everything. It will change more than once. Then differentiating the denominator, the power will go down, which is 2. Derivative of x squared is going to be 2x, so the result will be 4 of x. So this guy is 4 of x times the bracket, which is 1 plus x squared y squared. I can simplify stuff by taking 1 plus x squared y squared from the denominator and from the denominator. And this how I will have 1 plus x squared plus y squared to the power of 3. And on the other hand, I will have negative over 2 times 1 plus x squared plus y squared. And for this guy, I will have a positive of a 4 times 2 of an x, okay, which is going to be an 8 of an x squared. So start rearranging and simplifying the stuff. I believe you will have negative 2 then plus a 6 of an x squared minus 2 of an y squared, and it is divided by 1 plus x squared plus y squared to the power of 3. And once more, please try to be arranged as much as possible and gather the things very carefully, because usually there is a lot of mistakes will happen due to the sign conversions and the numbers that are added up once you start your process step by step. In a similar manner, I will try to get f y sub y, which means that I will differentiate this guy f of y another time with respect to y. So I will use this 4 exactly like what I did. So once more it's going to be to the power of 4. 1 plus x squared plus y squared. I will differentiate the denominator, which is going to be simply negative 2, times the denominator, which is going to be 1 plus x squared plus y squared to the power of 2. And once more, I will start leaving the denominator as it is. So it's going to be a negative for a negative over 2y. And once more, starting to differentiate your denominator the way you are used to. Don't you forget that we are making this dirty with respect to y. So it's going to be a 2, this is the 2, times the 2 over y of y squared, times 1 plus x squared plus y squared. That's the derivative of the denominator. And once more, I will try to simplify things as much as possible. So I will start with this bracket, taking this bracket as a common from everything. So I will have now a negative 2 times 1 plus x squared plus y squared. And in a similar manner, if you remark, I have a positive 2y times 2y, which is going to be 4y squared, times 2, you will end up having 8y squared. Exactly like what's happening with the x part, divided by 1 plus x squared y squared to the power of 3. So simplifying your life, it's going to be a negative 2 plus, minus 2 of an x squared, then plus, I believe, 6 y squared, and all of this y plus x squared plus y squared to the power of 3. Don't forget that I will need a substitution in the neighborhood of the point 0, 0 as I'm doing Maclaurin expansion. Once you do so, I will